Good day, my students. Welcome to Mr. Gavin's class, and today we are going to be learning about the physics of spinning. Let's get started.
Well, hi, class. Well, I'm sure you noticed I was going pretty fast on my bike there. Thankfully, these wheels get me where I need to go. But how fast was I going? Well, thankfully, we can figure that out.
So now let's kick things off with the basics of velocity. Here we can see how fast I'm going on my bike. Ooh, pretty zippy there, don't we think? So let's go ahead and pay attention to where exactly we started and where we stopped. Well, we can go ahead and pause right there, and we're going to notice that, we started about over here. That sounds fair. So then we'll let it finish, and we're going to end approximately there. So allow us to add a little mark there. One thing we need to know is what this d is, this distance is, when we're calculating velocity. Now, for velocity, what we need is v equals change over d over change over t. So we have a d, but we don't necessarily know how much that is. And for our purposes today, I'm just going to let you know that out there, that is 45 feet. Now, what else do we need? We need a t. And thankfully, right there, we have a t for us. So pay attention now. I'll play the video again, and notice when it starts and when I finish. So I'm going to go ahead and start at 35 seconds. And by the end of the time, I make it over to the second red line. We're at 40 seconds. It jumps to 41, but we were at 40 seconds. So with that, we know that our change in t equals 5 seconds. And we know from earlier that our change in d equals 45 feet. And what this is going to ultimately tell us is we're going to find our velocity by our change in d, 45 seconds, over, or 45 feet over our change in t, which is our 5 seconds. And after doing the math, what we get is a velocity of 9 feet per every 1 second.
But now, after talking about a review of velocity, everything we're going to be learning today is going to focus on just one wheel. Welcome back inside, everybody. It was pretty brisk out there. So you might be noticing, yes, we're talking about spinning today, and spinning in regards to many things. But if we take this wheel, for example, if I let go, it's going to fall, unless I give it a little spin. Then it no longer wants to fall. Why is that? Well, to help us out here, let's enlist my good friend, the Wheel of Fortune. Now, no one's going to be winning anything today, so I'm sorry for that. But here we have an arrow. And what this arrow does is it demonstrates that no matter where it is spinning, what position it's at, could be down here at this yellow, could be up here at this purple. What the arrow is going to do, for any point, will keep moving tangentially. So that at any given point, right here, its own personal arrow is going to be pointing tangentially, which means coming off the circle. And now, we can also think about this as a pizza slice with the angles being clearly marked here. So after we've looked at things tangentially, and we've looked at things with percentages of the circle, we can go ahead and derive our equation.
Now let's go ahead and talk about our angular velocity. So for this, what we're going to imagine is we have a spot right there, and we know it's going to be going tangentially. So this point will keep moving no matter where. First, let's go ahead and mark our middle of our circle. That way we can keep track. So if this were to keep moving, then what we see is right here, this guy might subtly drift down here on this part of the circle, but it's still going to keep that tangential movement. So here we notice that there's a change in not a distance, because we're working with circles, but a change in an angle. So the straight up equation for angular velocity is, and that's angular velocity. Angular velocity is a weird funky W symbol. It's going to equal our change in our angle over our change in our time, of course. So here we don't have a necessarily set in stone example, but you saw on the wheel earlier, and you can see a few more examples given the bike tires. But in this case, we're just going to go ahead and say that this time took 5 seconds again. So we're going to go ahead, change in t equals 5 seconds. That's a good enough time for an average experiment like this. And this angle change, well, let's just go ahead and imagine that up here, it's at 0 degrees. Straight up, we'll call that 0 degrees. Although it'll be different in your physics course, this is just to simply get that idea in your head. And if we were to measure this angle right here, what we're going to say is this is about 30-degree angle. So if we continue and we finish our angular velocity equation, our change, our theta, as we call that triangle change symbol, our theta is going to equal 30 degrees. So what that means is we've changed 30 degrees in 5 seconds. So our overall angular velocity, just for this class purpose, is going to be 6 degrees per second. That's how fast this angular velocity is moving.
So, going back to how we were talking about things moving at a tangential motion compared to the circle, let's take this pink wooden ball at the end of the string. No matter when I spin it, what that ball is going to be doing is it's going to be traveling tangent in the path it would take with the circle. If I let go, it's not going to continue out straight, and it's not going to continue to curve along with the circle. It will move tangentially to where I will release it, so we know I left it that way. So clearly that ball was moving tangentially that way when I let go, but what was keeping it there? Well, of course the string was. We call this string a centripetal force. We experience centripetal forces all the time. Gravity, right now, a centripetal force is keeping the moon in orbit with the Earth, alongside the rope keeping the ball. Or if we take this glass and we put the ball in the glass and we spin it, there's a centripetal force that is keeping that ball from going along and flying outside. That would be the glass in that case. And now what we're going to do is we're going to take a cup and we're going to fill it with water. This is at the end of a string. Careful, this is mighty dangerous if you don't do it safe enough, but if we go ahead and start spinning it, the centripetal force is keeping the water inside, and it's still rotating. And for those of you who don't believe, there was liquid in that cup. However, some of you still may be wondering, how does angular momentum keep us more balanced, for instance, on the unicycle? Well, for that, we're going to turn to a gyroscope. Now, what gyroscope literally means is scope the gyration of the Earth. Because if we let it go, pull the string, and pick it up on this board, even if the axis it changes on shifts, what the gyroscope is going to do is still stay in its given plane straight up and down. And do you notice how its angular momentum will keep it spinning very, very fast and keep it balanced, much like a basketball player keeps it on their finger. We've run out of time for this class, students, but join us next time as we use this equation to figure out why I spin faster with the books closer.
Lastly, I would just like to remind all of you to take the Google form after this. It really helps me understand how much you guys took away from this lecture. It's only 5 questions, so please remember to do that right after this. Thank you, and have a good rest of your day.